All right, today we're going on a bit of a data treasure hunt. We're on a mission to find those hidden patterns, the secret groups lurking inside our data. And to do that, we're going to look at two of the most popular tools of machine learning, k-means and DBSCAN. They both try to solve the same problem, but they do it in completely different ways. So let's dive in.
So picture this. You've got this huge cloud of data points. At first glance, it just looks like a total mess, right? A chaotic sea of dots. The big question is, how do you even begin to find the real, meaningful groups that are hiding in there? This is the exact problem that clustering algorithms were invented to solve.
Now, the technical name for this whole mission is clustering, and it's what we call an unsupervised technique. That's really just a fancy way of saying we don't know the right answers ahead of time. We're not telling the computer what to look for, we're just giving it the raw data and saying, hey, you go find the similar stuff and group it together for me.
Okay, so let's meet our first detective on the case, k-means. This one is super popular and for a really good reason. It's straightforward, it's fast, and honestly, it's usually the first thing people try when they need to find some groups in their data.
So how does this thing actually work? Well, k-means is what's called a centroid-based algorithm. The main idea is that it tries to find the center of gravity for a handful of groups. And that letter K in the name, that's just you telling the algorithm exactly how many clusters, how many centers of gravity it should go look for.
The process itself is actually pretty clever. First, you pick your number of clusters, your K. Let's say we pick 3. The algorithm then just plops down 3 random centroids, or centers, right into your data. Then, for every single data point, it asks, which center are you closest to, and assigns it to that group. After that, it finds the new center of each of those new groups, and it just does that over and over again. Assign, recalculate, until the groups just stop changing.
And that simplicity is its greatest strength. K-means is super easy to get up and running, and it's incredibly fast, even on really big data sets. But, and this is a big but, it has some major weaknesses. For one, you have to know how many clusters you're looking for before you even start, which is often a total guess. And its biggest weakness, the one that really sets the stage for our story here, is that it assumes all the clusters are basically round little blobs.
So what happens when that assumption is just plain wrong? What happens when the patterns hidden in our data aren't neat, perfect circles? Well, this is where our simple, trusty tool can get us into some real trouble.
Let's really hammer this point home. K-means is basically programmed to think in circles. It's always trying to find what are called globular clusters. It wants to draw a circle around a bunch of points and find the middle. And look, that works great when your data actually looks like that. But when it doesn't,
you get this. And this visual is just perfect because it shows you the problem so clearly. On the left, we've got data that's shaped like 2 interlocking crescent moons. To our eyes, it's obvious there are 2 distinct groups, right? But k-means, because it's only looking for those round blob-like centers, completely misses the point. It just chops the data right down the middle and gives us 2 groups that make absolutely no sense.
And that brings us to the next logical question. If our go-to, everyday tool can't handle these more interesting, irregular shapes, what are we supposed to do? How do we find clusters that might look like moons or spirals or, anything that isn't just a simple circle?
And this is where our second detective comes in, DBSCAN. Now, instead of looking for the center of a group, DBSCAN has a totally different strategy. It acts more like a neighborhood detective, walking around and looking for areas where all the data points are packed super close together. For DBSCAN, it's all about density.
Okay, the full name is a bit of a mouthful. Density-based spatial clustering of applications with noise. But that name tells you everything you need to know. It finds clusters by connecting points that are tightly packed together. And, this is a huge deal, it's smart enough to identify points that don't seem to belong to any group and label them as noise or outliers.
So how does it decide what densely packed actually means? Well, this diagram shows the 2 key ideas that make the whole thing work. The first one is called epsilon, and you can see it here as the radius of that circle. Just think of it as a search area around every single point. The second is min_samples. That's the minimum number of neighbors a point needs to have inside that epsilon circle to be considered important. If it has enough neighbors, we call it a core point, and that's the seed of a new cluster.
Let's just break that down one more time. Epsilon, or eps, is the size of that search radius, your personal space bubble. Min samples is basically the popularity contest. If a point has at least that many friends inside its bubble, it gets labeled a core point, and the algorithm starts building a cluster right there.
So let's put these 2 algorithms head to head. The differences are pretty stark.
For cluster shape, k-means assumes they're all circles. DBSCAN, it'll discover pretty much any shape you throw at it. For the number of clusters, k-means makes you specify the number beforehand. DBSCAN figures it out all by itself. And maybe most importantly, k-means forces every single point into a cluster no matter what. DBSCAN is smart enough to say, hey, this point over here doesn't really belong anywhere, and just marks it as noise.
Okay, so at this point, DBSCAN sounds like a superhero, right? It handles weird shapes, it finds the right number of clusters on its own, and it deals with outliers. But, every hero has their kryptonite. DBSCAN isn't always the perfect tool for every single job.
Here's its main weakness. DBSCAN uses one single global setting for density, that one epsilon value we talked about. And that means it kind of assumes that all the clusters in your data have a similar level of packedness. So it can get really confused if you have one cluster that's super dense and tightly packed, right next to another one that's much more sparse and spread out.
And you can see that problem perfectly on this slide. Look at that data on the left. You can see there are clusters, but they have very different densities. Because it's locked into one density setting, DBSCAN really struggles to identify all of them correctly. Now look to the right. That's a more advanced algorithm called HDBSCAN that was specifically designed to handle this problem, and it just nails it.
But even with that limitation, DBSCAN is an absolute powerhouse in the real world. I mean, it's used for all sorts of cool stuff. People use it to track thunderstorms as they evolve, because you never know how many there will be. It's fantastic for geospatial analysis, like finding hotspots of population density in a city. It's also a key component in fraud and anomaly detection, and it's great for finding groups in really complex data after you've visualized it with tools like UMAP. And that really brings us to the most important takeaway of all this. There's no single best clustering algorithm. It just doesn't exist. K-means is awesome for fast, simple, round clusters. DBSCAN is your hero for complex shapes and noisy data. The real skill is knowing how to look at your data first, understand its characteristics, and then choose the right tool for that specific job.
So the next time you're staring at that chaotic sea of data points, take a second. Think about its hidden structure. Are you looking for simple blobs, or could there be some weird, interesting shapes lurking in there? Your data is messy. Which detective are you going to hire? The center-seeking k-means or the density-hunting DBSCAN?